Imagine a 7,000-ton machine drifting through total darkness. In the abyss, sound travels faster and further than it does in the air. A single dropped tool in the galley generates a signature loud enough to draw an enemy torpedo directly to your position. Survival starts with the hull, 100 steel pressure hull. On the left is the vessel at the surface. On the right, it's at 1,000 feet deep. The steel isn't perfectly rigid. As the red arrows indicate, the immense weight of the water physically compresses the hull inward, causing the entire submarine to shrink in diameter as it dives. This compression forces a reaction from the internal engineering. Every floor, pipe, and bulkhead must be designed to flex. If the internal supports remained rigid while the outer shell moved, the hull would simply snap the structural frame in half. Withstanding that pressure is the first requirement of deep-sea operation. The harder challenge is moving this compressed, nuclear-powered skyscraper through the water in total silence. Look closely at the exterior of a modern submarine in dry dock, and you'll see thousands of dark, rubbery blocks applied over the steel hull. These are anechoic tiles. While they might look like armor, they are not designed to simply bounce enemy sonar waves away from the ship. Their actual function happens at the molecular level. When a sonar wave hits the grid, the rubber is engineered to vibrate, converting the kinetic energy of the sound into heat. The sound wave effectively dies inside the material. By neutralizing the sound wave, the submarine fails to return a signal. On an enemy's sonar screen, this massive machine appears as an invisible hole in the water. External stealth is only the beginning. The louder threat comes from the nuclear propulsion plant, the system filled with moving turbines, gears, and high-pressure pumps. In early Cold War designs, engineers bolted these components directly to the hull. This allowed every mechanical vibration to transfer through the metal and out into the ocean, broadcasting the sub's position to any surface fleet in the area. Modern subs use a technique called rafting to isolate that noise. The entire engine room is placed on a massive internal cradle. It's suspended entirely by isolated springs and rubber mounts, meaning no part of the engine physically touches the outer hull. Rafting creates a structural paradox. It allows a violent nuclear reactor to operate at full power while the surrounding hull remains acoustically dead. Even with an isolated engine and a rubberized hull, moving forward creates a distinct signature at the very rear of the vessel. When propeller blades spin quickly, they create areas of extreme low pressure along the trailing edges of the metal. The pressure drops so sharply that the water boils at room temperature, forming millions of tiny vacuum bubbles. This is cavitation. When these bubbles inevitably collapse, they create a sharp, violent crack. That scream can be picked up by hydrophones from 50 miles away. Stopping that noise requires extreme precision. In the 1980s, the Soviet Union used illicit 9-axis milling machines, acquired through the Toshiba Kongsberg scandal, to produce blades with perfectly curved geometries. This millimeter-scale adjustment was enough to significantly delay the onset of cavitation. Modern designs have largely moved toward shrouded pump-jet propulsors. By surrounding the blades with a nozzle, engineers can manipulate the fluid dynamics to compress the water, preventing those vacuum bubbles from forming, even at high speeds. Global espionage was fought over the curvature of these blades, all to prevent a single bubble from collapsing. Beyond the hardware of the ship, commanders have learned to use the ocean's natural environment as active camouflage. The ocean is divided into distinct thermal layers. When a surface ship sends a sonar ping down, it hits a sharp temperature drop-off called a thermocline. The density shift is so extreme that it acts as an acoustic mirror, reflecting the sound wave back toward the surface and leaving anything below it completely hidden. Hiding under that layer also means the sub can't hear the surface. To solve this, the submarine trails a 2-mile-long fiber-optic towed array. This sensor line penetrates the thermocline, allowing the crew to monitor the surface while they remain invisible below the thermal ceiling. A modern submarine isn't just a vehicle, it's a multi-mile-long nervous system that maps and exploits the thermal geometry of the abyss. Engineers have pushed acoustic stealth so far that it has created a new liability. Modern submarines have become too quiet. The deep ocean is naturally filled with shifting currents, ice movements, and marine life. AI sonar networks no longer search for a distinct engine noise. They search the background chatter for an unnatural pocket of absolute silence drifting through the water. As acoustic hiding reaches its limit, sensors are moving toward non-acoustic detection. Satellites now scan the surface for the microscopic heat wake left by a reactor, or use lasers to measure the minute hump of water pushed up by a hull moving thousands of feet below. While these hull coatings and engine mounts push the limits of physics, the era of absolute invisibility is ending. Space is running out to hide, making deep-sea data cables the new exposed frontline of underwater conflict.